Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about NASA's Europa Clipper mission. So let's dive deep into it. So this mission is a probe for studying Europa, one of the moon of Jupiter. Now, here's the deal. This puppy is a flagship mission, meaning other projects would be cancelled to keep this alive. So money is no object. How much? Well, $5 billion. So yeah, this is expensive project. $5 billion mission. Now the idea is it's gonna study basically the Europa using flybys. It's not gonna do orbiting of Europa itself, but do flybys. I'll explain why it has to do flyby rather than doing orbiting, but that's the intent of it. And it's gonna orbit Jupiter. And it's so far, when I'm making this video, so far one of the largest spacecraft ever made by NASA for planetary study. There are other things that are bigger like ISS and all that, but those are for different things. This is like, go there and study it. This puppy is huge, like a basketball kind of huge, like a person is tiny compared to solar panel kind of huge. Like this is huge, like ludicrous, because it's a flagship mission, so money is no object. So they went all out. Now, why the heck you want to send a flagship mission with this size and this kind of cost to basically Europa? Well, Europa has one of the strongest candidate with our current understanding of solar system. That puppy has life potential, meaning it has water. Why do we want water? As of our current understanding, the reason why water is critical for life as we understand it is because of water's property classified as universal solvent, meaning you have stuff. But as long as stuff cannot make love to each other, it's not going to do anything. You need universal solvent. Water makes excellent universal solvent. So water is there, good. Chemistry is easy. It's easy to find almost everywhere. Okay, tidal heating energy, because again, life requires energy to drive. In case of Earth, solar energy is the primary source. Secondary source is thermal vents that are like, deep into the ocean. So we know for a fact that if you have water, if you have chemical, and if you have energy source, life can thrive. This puppy has all of those. Inside this ice crust, there is ocean inside. And how do we know it has energy? Because there is no crater mark. It's like, wait, why? Well, craters are formed here. Like we have seen enough of it. But it, like, because it's getting tidally conjugated, the shell keeps reforming. That's why shell has so many crack marks rather than crater marks. It has crack marks. So shell is active. That's how we know it's inherently warm inside. And with all our observation, all our study and analysis, it says that it has a subsurface ocean. We just do not know the proportions of it, meaning the ice is like few kilometer or 100 kilometer or like, ludicrously deep. So it's one of those things we do not have enough detail about it, but we know with our current understanding there should be a subsurface ocean. And not to mention, it does have volcanoes which spew out steam. So we know there is something inside that is liquid. So this is Europa Clipper, the best candidate we have on the solar system. So we are putting a flagship mission to study this puppy, and a huge puppy. Now, what about the propulsion? Now, propulsion, it has a bit of a messed up history, but right now it's going to be launched using SpaceX Falcon Heavy, this puppy basically, on October 2024. Now, if it gets delayed, the backup windows are very close to each other because it does require gravitational assistance, meaning if they get pushed because of weather or technical fault, the mission would be in jeopardy. And like it might require to wait another few years. That's bad basically. Now it's going to take 5.5 years to transit from Earth, from launch date to actually getting captured by Jupiter. And it's not fast enough to do that. Basically, this puppy cannot dump enough energy to do that directly. So it has to do gravitational assisted maneuver 2 times. One time it has to do that on February 2025 from Mars. Basically, it's gonna get you launch it, it takes that energy, then it comes at ying. It takes another energy, then how it gets the final delta V it needs. So February 2025 is going to make a flyby of Mars, and on December 2025 it's going to make a final flyby of basically Earth, getting the full oomph needed, and then it's going to reach to Jupiter. Now be mindful, you will be going fast, and this puppy is big and heavy, so how do you slow down? This has 2.7 ton of bipropellant inside. It's loaded, so it's gonna burn a majority of that in that instant to do a decel burn. Basically, from here to do a decel burn, it has to spend a lot of energy, and it has bonkers amount of thrusters, like 24 amounts of them. So it's going to consume that fuel, no problems. And the idea is why this is so convoluted is that it was not designed for this. It was designed for SLS. Now SLS is a heavy lift rocket. It's almost like Starship. Now the idea was that what if you have a 100-ton to low Earth orbit, but you put a 6-ton and you yeet it. So you can yeet very fast. So the target calculations were with SLS, you can eat this puppy direct injection burn in 3 years, meaning you launch, it goes to Jupiter, the end. But that cannot be done because again, this, while it is powerful, again, it is doing the mission, it's just not that powerful. So it does require a bit of nudge from basically Mars gravitational assistant and Earth's gravitational assistant. Well, that was the original design. Now, they did try to get SLS, but then realized SLS is a human-rated flagship project. So Artemis will always prioritize it. And because of the ludicrous amount of delay and the fact that it's a LOL project at this point in time, even Inspector General Office was like, yeah, we have to find something else. And paperwork was filed in Congress to like, hey, please allow us to look into other options. They looked into it. SpaceX Falcon Heavy was considered the cheapest option. It saved them around $1 billion to utilize this puppy. So that's the propulsion story. But that's why the mission is like 5.5 years for, well, generally, if you are targeting based on this, they would have made it much lighter. So they would have gotten a bit more oomph out of it. The time is high, like 5.5 years. It's high. So what about the mission? The mission is that a solar panel was selected because again, you are going that far, you may think, what about RTGs, radioisotropic thermoelectric generator? While those are awesome, but they are expensive. They require nuclear safety commissions and all that jazz, so very expensive. Although it would have been lighter. So they're like, okay, we're gonna get cheaper, but heavier. So solar panel was selected. Now there is a biggest problem whenever you want to actually study Jupiter, not just do a flyby like Voyager. When you actually want to study it, this puppy has a radioactive belt. This belt is bad. Like Earth has a radioactive belt, which we call Van Allen radiation belt. That's bad. This makes that look like a honeymoon period. This is brutal because again, magnetic field of Jupiter is beyond bonkers. It's like, so the amount of particle it traps is very high. So high radiation environment limits the ability of any electronics to last, meaning if you put electronics there in this high radiation environment, it's gonna age. Meaning, what does aging means? Basically, your capacitors, they are way too close to each other. The more high energy bombardment happens on that layer, the weaker the capacitor will become. Especially with memory chips. Memory chips are specifically vulnerable. And your transistors, again, on-off is basically changing one energy state to another when you want to, when you designed it to. But if high energy particle from outside goes wet, it will cause bit flip, it will cause corruption. And yes, planes have crashed because of it. And that's on Earth when we have a giant atmosphere to protect us. So we have learned it the hard way that radiation is very bad for electronics. Space radiation like this, yeah, it's gonna cook your electronics. So electronics that could have easily survived in deep space for decades would barely last a month here because it's so high radiation environment. So that limited the fact that if they actually tried to directly orbit Europa, they would have exposure would have been so high that unless they have like, you know, lead shielding, like God tier lead shielding, they will not have survived. So that's the reason why they have selected flyby rather than direct orbiting. If we had magical shield technology that is lightweight, we would have done direct orbiting, but as of now, we do not have magical shield technology. So that's why the elliptical orbit was selected. So the idea is you go as quickly as possible in the radiation belt, you get out of there as quickly as possible, and then dump all the data to Earth in safe environment, and your total exposure is minimized. So that's the intent of it. And to make sure, because again, you are still dipping into the radioactive pool, it has radiation vault, this puppy, the main armor, chassis, so to say. That puppy is aluminum zinc alloy, specifically formulated to withstand this puppy. It's 9.2 millimeter thick. It's thick. Like from a space point of view, that's thick. So it's a very, basically they are doing the best they can do with the system. And again, this is only allows them to fly by. And even with this, it will still be a degrading battle. So instead of degrading, if they did not had this armor cage, so to say, they would have degraded, let's say, in 2 years. With the cage, they may last 4 years. That's kind of deal. Because again, we actually have no idea how to survive long term in this high radioactive environment in space while you have weight constraint. That's like, we just do not know. That's why close flyby was chosen. Now here's the benefit part of it. Some of the close flybys are very close, meaning the crisscrossing that we are doing, we could be getting very close to the surface. Now because of the low gravity of the moon, whenever that volcano events happen, the cryovolcano, whatever you want to call it, the water ejects out, it goes out very far, very high, like 100-kilometer kind of high. This puppy can dip below it, meaning if we are lucky, in one of those slices, there would be a volcano that going whoosh, and then we can just drive through the plume. That would be the easiest way to actually sample the water that is under the surface. And yes, we know, because we have captured it in Hubble and all that, that there is a plume. It's just it's a basically trying to time a volcano. You cannot time it. Or maybe you could, once we have this high resolution map and this high level of technology studying this, maybe we figure out, hey, this is how it's gonna happen. So maybe, but again, that's not a guarantee. That's why they are not saying that we're gonna do this. It's like it could do that. It's like if we luck out, like let's say we are doing this jump to it, very close dive, it's like boom, everybody's gonna be party, but that's not guaranteed. But you will see, like radiation doses is brutal here. So that's why mission has such a weird design. Now, what about instrument? Well, because it's a flagship project, they went all out, and it's so in depth. I may need a freaking 40-hour-minute video just to make a sense of all the instruments. It's very high density. So, Europa Thermal Emission Imaging System. Basically, it's a thermal camera, but be mindful, all thermal cameras generally, humans are exposed to common people. They are generally one band thermal camera, meaning you take infrared, you stretch it. You have mid infrared in the center, you have long infrared in the later, and you have high infrared. Now, or like just infrared, basic infrared. So basic, mid, and long infrared. Now generally most thermal cameras only work in one band. It could be low, it could be mid, or it could be high. Now mid is available and high is available. So it has like much higher resolution thermal camera comparatively speaking. Now what could you see? Ideally, how the temperatures are working inside the core. And yes, it should work that. That's why they put such a high quality thermal camera. Ocean to near surface region. Yeah, basically that's the radar part of it. And that's why like the panels are so huge, because it actually allows them to space out the antenna, ground penetrating radar they have. The idea with that is that when you scream in high frequency, it goes through stuff. Now it has a fixed speed based on when it's going through basically vacuum, but the moment it goes through ice, speed changes obviously, but it goes through water, speed changes again. So based on basically if you are doing it correctly, you can actually figure out how deep is the ice, how deep is the water below the ice. You can get both of the data, because it also has another variable. The basically is changing the pattern of the radio signal. So you send radio signal, let's say polarization, one way of polarization, ice will depolarize it some way, water will depolarize it completely different way, meaning you will get clear signal. This is one item, this is second item, and you calibrate it based on Earth's data, where it's like, okay, ice gives this sort of scrambling, so to say, and water gives this sort of scrambling, and voila, ground penetrating radar from space. So you can do, and that's the primary reason, like there is a very good chance if all of these puppy work properly, we can claim Europa, where it's like, no, you are exactly like this without even drilling into it. And then it says mapping, imaging, spectroscopy. Spectroscopy is, it's one of the most common thing that you put there, spectroscope. And that is a Europa imaging system. Yes, it's optical. Again, you do want flagship mission, you do want some cool pics. It's expensive, $6 billion. You better have some 4K photos out of it. So, RGB photos out of it. Europa ultraviolet spectrograph. Be mindful, in simplest way I can describe it, it's a hyperspectral instrument. What does that mean? That simply means from very deep infrared to very high ultraviolet. It can capture all of it, not just optical, not just infrared, not just ultraviolet, all of it. So it's a hyperspectral system. Again, not one instrument that is that hyperspectral. It would be very expensive, but they have enough that they are covering the whole electromagnetic spectrum. And Europa Clipper magnetometer. So there is a long stick coming out of it. That stick is this puppy. That puppy is magnetosensor. You have to understand, Jupiter's magnetic field is huge, but Moon has its own magnetic field, and interaction between these two things, if you can study in high resolution, you can figure things out. And magnetic field and water, they have a relationship to it. If you can figure it out, that's a lot of high resolution data below the surface. So that's another desirable aspect. Plasma instrument of magnetic sounding, PIMP. And then you have mass spectrometer for planetary exploration. Basically, it has a system somewhere here. It's like mass spectrometer. That puppy is supposed to go through the plume. If we are lucky, and again, there will be dust because it has low gravity. So even if a volcano, let's say when you are in the far side, volcano happened, that water will not fall down very quickly. It's not Earth. Gravity is very weak. Heck, it's weaker than Mars. Mars, why I was saying, Moon. So it will last there for a long. So you can go through it, and there is a very good chance there will be a mild atmosphere. Now let that be clear. PSI is not high enough unit for measurement. That's like ppm, parts per million, or ppb, parts per billion. But there will be enough oomph there. There will be enough dust. There will be enough stuff there that if you have a sensitive enough instrument, you should be able to sample it. And that's the whole idea of it. Why does it has so many spectrometers? Like there's supposed to be enough dust that we should be able to get some signal out of it, where it's like what kind of salt we are dealing with. So surface dust analyzer, that's the whole point. And now here's the, it has a lot of things, but here's the, your mobile phone has almost this kind of oomph What's the limiting factor? Why don't we get 4K video out of it? Yeah, is the data link, basically this puppy. Now RTG would have made it bit better, whereas the right now the solar panel is a fixed energy, which is not a lot, because again it goes into shade, it goes into occlusions. Basically here sun is here, you are behind it, you are going into eclipse, so occlusion limits your output. So at that time you will have to rely on batteries. RTG removes all of these issues, so that time the radio could be like, I am like full 100-watt power. So radio is limited. That means how much oomph you have in this is very limited, and how much capacity you have in deep space network, that's already saturated. So that also another limiting factor. So all these things limiting factor creates a scenario where it's like, yeah, we can do all the sensors, all the instrument out there, all of these puppies are awesome. It's just that you can't dump data fast enough. So idea is you go in, you study it in like few minutes, and then when you come out, you take 7 to 10 days to dump it out. So that's why it has so many instruments. So radio distance, and you must have seen that NASA is working a lot into laser communication. That's the reason. Laser in principle, and again early testing proves this, that if you have 100-watt for radio communication, 100-watt for optical communication, 100-watt of optical laser will give you far higher bandwidth and far more throughput. Basically how many gigabytes you can transfer based on 100-watt of radio versus 100-watt of laser. 100-watt laser is 10,000 times better, like, because again the beam divergence is much better, and signal to noise ratio is also much better. So that's the reason why we are working our ass off, but this does not have it. So it's limited still by ancient technology of radio. Now that's so far so good, all that, but it also has a boom event planned. Now you have to understand, when we actually realize that there is water on these planets, we realize very seriously we cannot contaminate this, because again from a biological point of view, from a medicine point of view, if you want humanity to grow, if you can give humanity scientists, whereas like here's a different path for life, the amount of growth and development will happen to humanity would be god tier. So you cannot contaminate it. So this is the water volume on Earth. This is the water volume on this small puppy. It's larger. So we learned it the hard way, that we cannot contaminate this. No matter how good your testing system is, no matter how much you trust the sterilization of radiation, you cannot trust it. You cannot count on it. So the idea was decided that you're gonna yeet these things into the gas giant, where we do not have a surface to crash. You just have compression to go. So basically this puppy, and there's a very amazing Nat Geo documentary about this. Like it's fighting, it's like they will make you feel emotions. I have linked it down below. Like it actually was fighting. They commanded make sure to maintain the handshake with Earth's deep space network to best of your ability. Like it kept sending signal while it's going through the atmospheric drag. The thrusters were like firing all out, and they said like the boom, if they had a technology of detaching the boom, it could have survived much longer. The boom was like creating unnecessary drag, but it did amazing job, where it's like, I'm going, this is my last fight, but it's like, one last ride, like actual one last ride. So that was awesome. So the idea is that we have to crash it before we lose control, because you are going through high radiation envelopes. You will reach a point where it's like, let's postpone it for 1 year, and 1 year later, yeah, we ran out of computer control. That could happen, and that will happen. The solar panels is also degrading exponentially faster compared to any other mission. So there is a very hard line. So you have 5.5 years of cruise, safe environment of deep space, and then you have 4 years of a high radiation environment, and they're like, no, we have to poof it after 2034. We have to poof it. So the idea is we cannot contaminate the moon itself, so it must crash somewhere else. Now there is a proposal. Let that be very clear. It's a proposal. You cannot guarantee it, this is what will happen, because it does require something else also be there. The idea is that what if we crash it in Ganymede? Because it's orbiting Jupiter, it can change its direction from one moon to another and yeet into Ganymede. Now, like, why would you want to crash it to Ganymede? Well, Ganymede is an interesting object. Does not have water, and like it does have water, but very down below. And we are like, we consider it very safe, active volcano region. So we are like, okay, what hitting it is like drilling there. It's like, if you can do that on a orbital velocity, that's like a lot of scientific data, but here's, you need an observer. Thankfully there is JUICE, Jupiter's Icy Moon Explorer. So that project is second in construction, that's supposed to be launched. So if things line up, you could have a scenario where once the mission is over, it does its final plunge into Ganymede, and there is another spacecraft capturing the whole scene. Lot of detail could be gleaned from that. So that wabam, it should create enough of a plume, because it's a big heavy thing. Even with a reduced mass of like 3 tons, it's still 3-ton object. 3-ton object traveling at that kind of delta V, wabaming it, it's a lot of boom. So that boom would give us a lot of data, like maybe even dig into like 1 meter or 2 meter deep. So And not to mention, the plume will also not fall very quickly because it's a moon, not Earth. So plume will be there in space for a very long time, so we can study it quite effectively. So that's a far out plan, but there is a room for that. So they may crash it into gas giant if juice is not ready. But if juice is ready, things line up, stars align, they could be like, okay, wabam it into Ganymede. I would like to see that, but that's like 2034. I might not have hair left by then. So it has a like bombastic ending planned. So this was my presentation on Clipper, Europa Clipper mission. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.